Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to the subject Electromagnetic Field Theory. We are with chapter number 11, that is plane wave reflection and dispersion. Up till now, the two terms of this particular chapter title, that is plane wave reflection and dispersion, both we have covered. For plane wave reflection, we first of all started with the two general mediums that are separated by the boundary interface, and at this particular boundary interface, we considered the direction of propagation of traveling wave, that is incident wave, to make 90-degree angle with the boundary. Hence, the topic was uniform plane wave reflection from the boundary separating two general mediums at normal incidence, normal meaning the perpendicular. Followed by, we have taken the second medium to be the perfect conductor. So for practical conductors, we have solved the numericals. The perfect conductor ideally will reflect everything into the medium 1 again. We have seen the standing wave ratio. We have seen the wave reflection at multiple interfaces. We have seen the electromagnetic wave reflection of oblique incidence type also, followed by the dispersion and its corresponding problems. So it is time to conclude this chapter, that is plane wave reflection and dispersion, by practicing the miscellaneous problems 1 and 2. So let us first of all have miscellaneous problem 1. So this is our problem statement. Let x equal to 0 is the boundary between two perfect dielectrics. For x less than 0, mu1 equal to mu0, epsilon 1 equal to 3.6 pi into 10 to the power minus 12 farads per meter. Sigma 1 is equal to 0, and for x greater than 0, mu2 is equal to mu0. Epsilon 2 is equal to 14.4 pi into 10 to the power minus 12 farads per meter. Sigma 2 is equal to 0. If EY1 having the positive sign over its head as a function of t is equal to 60 cosine of 10 raised to power 9t minus beta 1 x volts per meter, find. We have to find from A to F. So in A we require beta 1, in B we require the incident magnetic field intensity as a function of time. In part C we require EY1 to the power minus, what is it, we can see here, so it is also a function of time. Beta 2, then EY2 having the positive sign, so it is also a function of time. And finally SWR means standing wave ratio. So first of all, as per the given details, we will see what exactly the boundary is, which two particular regions are separated by this particular boundary. So boundary is the surface at x equal to 0. So as per the chapter number 1 from this particular subject, that is vector analysis, we have seen for the Cartesian coordinate system, x equal to 0 means it is nothing but YZ plane. So here onto this horizontal orientation, if we take x-axis, so onto the right hand side we have the positive x direction towards the positive infinity, and onto the left hand side the negative infinity of x, hence the side is x equal to, minus 1, minus x direction. So this is our x equal to 0 plane. So this is nothing but the YZ plane. This is our boundary. So this particular boundary separates two perfect dielectric mediums. So these are x less than 0 and x greater than 0. So this is our region 1. Here we can mention x less than 0. This is our region 2 on this side. This is x greater than 0. So corresponding permeabilities, permittivities and conductivities of the region 1 and that of the region 2, here we can show it into this particular diagram, and then we shall proceed further. So this is for region 1. We have the permeability, that is mu1 is equal to mu0. Epsilon 1 is given by 3.6 pi into 10 raised to power minus 12 farad per meter. Mu0 is the constant term, that is known 4 pi into 10 raised to power minus 7 Henry per meter. Along with the conductivity into the region 1 or medium 1, we can say it is equal to 0 for the region being the perfect dielectric. So on the another hand, we have mu2 is equal to again mu0, the same value. The epsilon 2 is with different value, that is 14.4 pi into 10 raised to power minus 12 farads per meter, and sigma 2 conductivity is also equal to 0 for the perfect dielectric medium. Now for the medium number 1, the region number 1, we have EY1 to the power positive sign as a function of t. In general, we have some conventions to represent the traveling wave, reflected wave, transmitting wave. So incident wave or traveling wave, if we say, if this is propagating towards the positive x direction, so we generally have the plus sign to its particular head. So x being the direction of propagation, as per the Poynting theorem, we know that the direction of propagation will be perpendicular to the orientations of electric and magnetic vector fields, and these two are also mutually perpendicular. So if x is the direction of propagation, the options with the E are either y or z direction. As per the problem statement, we have been given the y orientation for E. So as it is in medium 1, we have this EY into medium 1 and proceeding towards the positive x direction, hence we have the positive sign. It is a function of time. With the change of time, the magnitude can be varied for the electric wave. So similarly, we can have the h component also. So direction of propagation. So the direction of propagation towards the positive x-axis, y orientation for E. So h will be left with the x orientation. So for the medium one, we can give the suffix 1. It will also be the function of time t, and proceeding towards the positive x direction, we have to put plus sign over its head. This is also one convention used for representation of incident, transmitted and reflected wave. So for reflected wave, if we have such a portion, and for transmitted wave, so for transmitted wave, we again will be having EY component and HX component, but this is into medium 2, region 2, the suffixes 2 have to be given. These are again proceeding towards the positive direction of X, so we shall be giving positive polarity over their head. They will be again the function of time. Now the reflected wave is having a reverse direction, so instead of the positive signs over their head, we can show negative signs. So HX in medium 1 will have negative sign over its head, and EY1 T will have negative sign. So negative sign represents the reflected wave, the positive sign represents either it is incident wave or the transmitted wave. So to distinguish between, if the suffix is 1, it is incident wave, if suffix is 2, so that time it is transmitted wave. So here we are given EY1 as a function of t by 60 cosine of 10 raised to the power 9t minus beta 1x. So the phase shift constant into the medium 1, beta 1 is there. So it is with the minus sign, x is there. So means the direction of propagation of wave is along positive x direction. So magnitude we have, and we have omega. So EY1 as the incident wave we are given. So what are the things asked in this particular miscellaneous problem 1? So first of all, we have to determine the value of beta 1. Beta 1 is the phase shift constant into medium 1. So let us start one by one. So for beta 1, we shall begin. So here we have the representation. First of all, I mentioned EY1 suffix EY1 as a function of t, and this is the positive sign. So this is 60 cosine of 10 raised to power 9t minus beta 1 x. So it is in volts per meter. So this particular given data implies omega, that is angular frequency, is equal to 10 raised to the power 9. This particular value. The SI system of units is radians per second. Now we require beta 1. So beta 1 is given for the perfect dielectric region, omega under root mu into epsilon. For medium 1, for beta 1, we shall designate mu1 epsilon 1. So getting back to the diagram, we have the mu1 and epsilon 1 given by these particular values. So we can substitute them along with the omega. Therefore, the beta 1 will be obtained as, so beta 1 will be equal to 10 raised to the power 9 in multiplication with the square root. Here mu 0 is 4 pi into 10 raised to the power minus 7 into the epsilon, we can mention 3.6 pi into 10 raised to the power minus 12. Therefore, we obtain beta 1. So, beta 1 is holding the value 1.2 pi. This is nothing but 3.7699. So, as phase shift constant is there, SI system of units is radians per meter. Hence, I outline this particular beta 1. So, this way, part A of this particular problem statement for miscellaneous problem 1, we have the answer. So, beta 1 we have. So, beta 1 is having this particular value. Now, we shall attend the second part, that is B part, the incident magnetic field intensity as a function of time we require. Now, in the diagram, we have already discussed the reflected portion, the incident portion, and the transmitted portion from the electromagnetic wave. So, here we require incident magnetic field intensity as a function of time. So, magnetic field intensity is denoted by H. Incident one will be into the medium one, and the positive sign will denote the incident wave. So, Hx1 as a function of t is required to be calculated. We have Ey1, that is incident electric wave. So, with these particular things available, we shall proceed to get the answer for part B. So, from the intrinsic impedance, so intrinsic impedance is the ratio of magnitude of electric to that of the magnetic wave. Hence, for the medium number 1, we shall write eta 1 will be equal to, so it will be Ey1 plus function of time. In this diagram, as we have the direction of propagation x, so as per the TEM, that is transverse electromagnetic wave, we have to make them z. So this is z. So z direction is perpendicular to that of the y, and it is also perpendicular to that of the direction of propagation x. So it should not be hx1, it should be hz1. Herefore, here we mention it is equal to h suffix z1, the positive sign, to denote the incident wave as a function of time. So from this relation, we can make hz1 as a function of t having the positive notation. It will be given by Ey1 positive as a function of t divided by the intrinsic impedance eta 1. Now, intrinsic impedance eta 1 can be calculated by taking the ratio of under root. Here we have mu 1 upon epsilon 1. So, therefore, the hz1 for the incident wave function of time, so it will be the ratio. So, 60 cosine of 10 raised to the power of 90 minus the beta 1 value we substitute 3.7699x divided by the intrinsic impedance has to be substituted. So this is the under root ratio of, so mu 1 will be 4 pi into 10 raised to the power minus 7, and epsilon 1 will be 3.6 pi into 10 raised to the power minus 12. So we have right hand side substituted with the all values. Hence, hz1 as a function of t can be obtained. So RHS, it will become 0.18 cosine of 10 raised to the power 9t minus 3.7699x. So as this is magnetic field intensity as a function of time, we must mention the SI system of units, that is ampere per meter. So this is the required answer for part B into the problem statement. So this is our problem statement. We required the incident magnetic field intensity as a function of time, and we have this particular answer. Now the next part is part C. We require Ey1 as a function of t, and minus sign is given to this head. Therefore, it is the reflected wave into the medium number 1, so that we have to calculate it. So in order to calculate the reflected wave for part C, we will be taking the help from reflection coefficient. Reflection coefficient is denoted by gamma suffix r, and this reflection coefficient is the ratio in general ER divided by EI. EI denotes the incident wave, ER denotes the reflected wave. Here, as per this problem statement, we have the notations for the incident electric wave. We can have it is EY1, the positive sign over its head, and here it is EY1, negative sign over its head for the reflected wave. Both reflected and the incident waves are lying into the medium number 1. So we have seen the formula of this reflection coefficient in our previous videos in terms of intrinsic impedances. So it is given by eta 2 minus eta 1 divided by the addition of the two, eta 2 plus eta 1. So what are these eta 1 and eta 2? So for determination of that one, we will take eta 2 under root of, it will be mu 2 divided by epsilon 2, and eta 1 will also be under root, it will be mu 1 divided by epsilon 1. So substituting the values here, for eta 2 we get under root 4 pi into 10 raised to the power minus 7 divided by, it will be 4.4 pi into 10 raised to the power minus 12 here. So this shall give us the value 166.6666. So intrinsic impedance measured into ohms. So eta 1 will be given by under root, it will be 4 pi into 10 raised to the power minus 7 divided by epsilon 1 value is 3.6 pi into 10 raised to the power minus 12 here is equal to, we obtain the value 333.3333 4 times. So it is also to be into the ohms. So eta 2 and eta 1 values we have obtained, that we can substitute it into this particular formula to obtain the reflection coefficient. So therefore EY1 in negative sign divided by EY1 in positive sign, we can obtain 166.6666 minus 333.3333 divided by, the magnitude will be added here. So here we make the addition of the two. So this gives us the result, that is minus 0.3333. So we have obtained the reflection coefficient. So it is this particular ratio EY1, that is having positive polarity, is incident wave. It is already available to us. Therefore, we can obtain, that is EY1 negative, that is minus 0.3333 in multiplication with this available EY1 positive incident wave. So this particular multiplication shall give us the magnitude. So EY1 minus the magnitude of the incident wave is equal to 60. So it shall give us minus 0.3333 into 60, which is equal to minus 20. So though it is reflected wave, it is electric field intensity representation. Electric field intensity representation is always in terms of volts per meter for the SI system. Therefore, as a function of time, we can make EY1 negative as a function of time. So it will be equal to 20 cosine of 10 raised to the power 9t plus it will be 3.7699 x into in terms of volts per meter. Here the sign change occurs due to the reverse direction of reflected wave with respect to the incident wave. So this is the required answer for the portion that we have part C. So part C answer is given by this value 20 cosine of 10 raised to the power 90 plus 3.7699 x in volts per meter. So three parts have been covered. We require B2, beta 2. So beta 2 is the phase shift constant into medium 2. So to obtain phase shift constant into medium 2, we take the formula for perfect dielectric materials. Beta 2, it will be omega under root mu 2 n2 epsilon 2. So we have all the three values. omega is equal to 10 raised to power 9. Square root will have 4 pi into 10 raised to power minus 7 as mu2, and epsilon 2 is 14.4 pi into 10 raised to power minus 12. So we have all the values. So this shall result into 2.4 pi. Therefore, we can mention beta 2, that is 7.5398. So as per SI systems, this should be in radians per meter. So I outline this particular result for part D. So part D is also covered. We require only two parts to be solved. So for part E, we have this into medium 2, the suffix is, so this is region 2, and plus sign. So this is the transmitted wave. This is the transmitted electric wave as a function of time we require. So for that purpose, we here take the help of transmission coefficient. So the transmission coefficient shall be the ratio, that is ET divided by EI in general. Here in this problem, it is nothing but EY2 positive divided by EY1 positive. Both have the same direction. It is either denoted by tau or again the capital gamma. So this is for the transmission, that is why the suffix will be capital T. So in terms of intrinsic impedances, we have it twice eta 2 divided by eta 2 plus eta 1. Here the directions of the components of electric that are along the Y, the magnetic along the Z, and the boundary surface at x equal to 0, we take the normal incidence, we get the normal incidence. So substituting these particular values, we obtain the numerator 2 into 166.6666 divided by, it will be the addition of 166.6666 plus 333.3333. So this gives us the result of the transmission coefficient to the value 0.6666. So using this transmission coefficient value, knowing the incident wave into medium 1, the transmitted wave into the medium 2 can be determined. Hence, we obtain the magnitude of that particular one. So EY2 positive is given by 0.6666 multiplied by 60. So this gives us the result 40. So it should be in volts per meter. So as a function of time, we can mention it EY2 positive as a function of time. So it will be equal to 40 cosine of 10 raised to the power 9t minus, it will be 7.5398 x into volts per meter. So this is the required answer for part E. So getting back to the problem statement, part E is also solved. It has this particular answer. And finally, we require SWR. So SWR means the standing wave ratio. Now here we have the reflection coefficient as well as the transmission coefficient. We know the formula for determination of standing wave ratio in terms of the reflection coefficient. So it is 1 plus magnitude of reflection coefficient divided by 1 minus again the magnitude of reflection coefficient. So substituting that one, it will be 1 plus 0.3333 divided by 1 minus 0.3333. Hence, the standing wave ratio SWR will be obtained with the value 2. So, standing wave ratio is actually the maximum amplitude of electric to that of the minimum amplitude of electric wave, or simply the electromagnetic wave. So, it is a unitless quantity. So, S is equal to 2 is the answer of F. So this way, for miscellaneous problem number 1, we had a concept of standing wave ratio, we had a concept of incident as well as transmitted waves, along with the time domain representation of these particular waves at the interface separating the two perfect dielectrics. So I hope the reflection of electromagnetic wave right at the interface between two perfect dielectrics is very much clear to us. In the subsequent video, we shall take the next for the miscellaneous problem number 2. So for getting such more information, and practicing more numerical statements for electromagnetic field theory, you can subscribe to Ekeeda channel. Thank you.